So thank you all for coming, and I must say it's a real pleasure to be here. I've met a lot of old friends and made a few new ones. I've been spending the morning in the lab and talking to some of the students here. So today what I want to talk to you is about two very disparate looking objects. This here is a black hole, which is a light trap, and this here is a steam engine. And some of you would be too young to remember what a steam engine looks like, but I think you might have seen old movies in which there are steam engines. So the main point of my talk is that these two objects, which look as different as a cow and a peanut, actually have something to do with each other. They have some things in common. That's the main burden of my talk. So if I like, I can stop here, and that's the end of the talk, that steam engines and black holes are related in some way. But the rest of the talk is going to try to elucidate on this point. So this is the plan of my talk. I'll spend about 15 minutes introducing the subject, a lightning introduction to relativity and black holes, and finally I'll come to this topic of order and disorder, which is in some ways the main purpose of this talk, and persuade you that black holes are warm, not cold objects but warm. And I'll have a very brief conclusion. I want to also thank Ananya, Rohan, Harini, Aditi, and Sidsha. These were students at CMI, and I'd gone to CMI to give this talk. And when I went there, I'd planned to show the lectures explicitly as demos. But many of those demos involve water. And sure enough, just like here, the facilities people will come running if you show dangerous looking experiments, which involve water and fire and things like that. So they help me to convert everything into videos. So right now, the worst that can happen is that the videos won't play. Okay, this is a cartoon drawn by my daughter, Roshni Samuel. And it has Einstein and the two equations which I will use in this talk. This one is E equal to mc squared, and this is E equal to h nu. Everyone knows this equation, which is the equation relating energy and mass. The second equation relates energy and frequency. These are the only two equations which I will use in this whole talk. So almost no equations, and I will use pictures, words, demos, analogies, and I'll apologize to those who wanted more from this talk. And I'd like to actually convey the excitement of this subject, which is extremely exciting, I think. But more important than the excitement, I'm hoping that some of the substance of the talk should be conveyed. I don't want it to be just a GWIS talk where you come and look at shiny objects and you go away feeling happy. I would like you to understand something about the subject. First, let me start with the speed of light. I think you all know that the speed of light is 300,000 kilometers per second. That's an extremely high speed. Light can travel 7 times around the Earth. We have all read this movie, we've all read the book or the movie by Jules Verne, Around the World in 80 Days. But light can go around the Earth in the blink of an eye. It takes 1.5 seconds to the moon. And you will agree that the speed of light is very large. So once I've secured your agreement on that point, I'd like to contradict you and say that actually the speed of light is very small, because it takes 8 minutes to get to the sun, 10 hours to get to Pluto, 4.5 years to the nearest star, 3 million years to the nearest galaxy. And there are some galaxies in the sky where the light departed from the galaxy when dinosaurs were still roaming the Earth. So light is extremely slow on a cosmic scale. Although we think of it as extremely fast on an everyday scale, it's actually extremely slow. That has the effect that when you look out into space, when you look deeper into the past, when you look further out in space, you're looking deeper into the past. And it's something like archaeology. You're learning about the past by looking at the things that you get now. Now, the theory of relativity basically acknowledges the fact that C is not infinite, but it's a finite number. And not only is it a finite number, it's the same no matter where you are. The speed of light is always the same, no matter whether you're moving at a certain speed or if you're moving with the Earth or Jupiter, you always measure the same speed for the speed of light. So the theory of relativity basically is an acknowledgement of the finiteness and the universality of C. I said earlier that I was going to use analogies in order to explain my stuff. So analogies relate new things to familiar ones. They're never perfect, but almost always useful. And Things like similes and metaphors are used by poets to describe what they want to talk about. And also doctors and lawyers, investment bankers, just about everybody uses parallels between one system and another in order to learn about new things. Now, the analogy I want to use is that sound is very much like light. Of course, it's not the same as light. There are many differences, but I want to talk about the similarities. Both travel at a finite speed. Both have vibrations at a certain frequency. The pitch of sound is like the color of light, and thunder is the source of sound, and lightning, which accompanies it, is a source of light. Apart from thunder, you can have voices like mine now, which you're listening to. You can have annoying horns of the kind I heard when I was coming from home to this place. Musical instruments, and here's an example. Source of sound. You might notice that I kept my fingers closed, but I produced 3 different frequencies from it. Four. Okay? So a fixed column of air can vibrate at different frequencies. Now that is something about sound and the fact that sound is a wave and it can fit into this pitch, into this length. Just like that, when you have electrons and atoms, electrons are confined in a small space, the space of the atom, and they too can have different frequencies. Yeah. So just by looking at sound in a flute, you can understand by analogy how atoms have different frequencies. Whenever you confine waves, they're only allowed to vibrate at certain discrete frequencies. Let me make this point a little bit clearer. I need a volunteer, somebody to come up, one of the students preferably. Yep. So what you were looking at is basically vibrations of a column of air, and you can see very similar effects in the vibrations of a slinky. Here also there are waves. You can see there are waves going up and down. For example, I could send a wave there and it's going to bounce back, just like light bounces off a mirror. Can you see the wave going up and down several times? Yeah. And what you were seeing was that in the flute, there was something like a fundamental frequency, and then there was higher harmonics and even higher harmonics. Yeah. So all these things, different modes of vibration of the slinky or the atom is what gives rise to different frequencies. So every atom has its own song, if you like, it's like a musical instrument. And you can find atoms at the other end of the universe, and when they put out their songs over there, you can hear the same songs over here. And from that, you can tell what kinds of atoms are present in the distant parts of the universe. And that led to many discoveries about the nature of the universe, the fact that the universe is expanding, and in fact, the fact that it's accelerating. All these things came out of that. So here's a picture of the different kinds of songs of atoms. This is a flame. Well, this is lithium. When you put lithium in a flame, it looks like that. And if you put copper in a flame, it looks green, bright green. And the Doppler effect, this is another demo which I have to skip over unless, yeah. So light from moving sources is shifted in frequency. And normally I show this demo with this swinging gizmo. And the advantage of this is that this is quite light, and I'm sure that the string won't break. But now Kripa has kindly volunteered to do the same demo with Firefox. Can you hear the change of frequency? Can you and point it towards them there? And this bunch here. Not me. Don't point it at me. Okay. Thanks. I think so. Everyone heard the effect. No? In fact, the safest person in the room was Kripa, because if it had gone flying out, one of you would have been hit, but she's fine. She would have been fine. No? So just like there's a Doppler effect with sound, light also shows a Doppler effect. And because of this, we were able to detect the cosmological redshift. Now, relativity tells us that c is nature's speed limit. You cannot go faster than light. When we disregard the speed limit, because it's so large, we end up with Newtonian physics, which many of you have studied in school. But when we acknowledge the speed limit, we are in the realm of Einsteinian physics, which is what we are talking about today. Most of this talk will stay Newtonian, but we'll use C finite. That's well built in the finiteness of the speed of light. Atoms emit photons, which are particles of light, and the energy of photons is related to the frequency of light by the formula which we already saw earlier. the one over here. Now, this slide actually represents the two revolutions of the last century. The first revolution was relativity, which is embodied in the speed of light here. And the second revolution is Planck's constant, which you see here, the proportionality between energy and frequency. These two revolutions happened and they really changed the way we look at the world. But it's been an incomplete revolution because these two revolutions have not joined together. It's like you had the communist revolution and maybe the green revolution somewhere, but you would like to join the two revolutions and come up with one grand revolution that combines everything. So relativity thinks of space and time as one object, and the way in which we convert them into one object is to use the speed of light to translate space into time and time into space. Space-time is the set of all events. For example, if I snap my finger here, that's an event. It has a location in space and it happened at a particular time. Similarly, for example, a firecracker going off at Diwali is also an event. It's localized in space and time. Now, time is normally measured in seconds and space in meters or centimeters. We can convert everything to seconds, and this is a consistent worldview, and this is the worldview we take when we are doing relativity. In special relativity, we go from space to space-time, which is the four-dimensional kind of structure, which we can draw a picture of. And the ultimate theory here is general relativity, where we go from flat space-time to curved space-time, and I'd like to illustrate those points as we go along. Let's start with the special theory of relativity. This was Einstein in 1905. Since C is finite and universal, it's the same for all observers, and you end up with the idea that space and time are really the same stuff, the same substance. And similarly, matter and energy are the same stuff. You can convert matter into energy. You can convert energy into matter. So bodies not acted on by any forces move uniformly in straight lines in this space-time. Bodies acted on by forces follow curved lines. So here's a picture of that. This blue stuff, let's think of as space-time. Here's a particle moving uniformly without forces. Here's another one moving uniformly for a while, then it gets hit by a force and it changes its speed, and then finally it goes straight up there. And this is something which is being acted on continuously by a force. And I plotted space here and time here converted into spatial units to make it look more like geometry. So we measure time in meters and we are in the realm of geometry. Einstein's theory of gravity is called general relativity, and gravity is described by a curved spacetime in which small pieces appear like the spacetime of special relativity. By piecing together two small flat tiles, you can produce a curved surface. Many of us have seen that. Even on a mountain, you can tile the surface with flat tiles and get a curved surface with slight inclinations between the tiles. Bodies follow the local straight lines, but because spacetime is curved, the bodies appear to follow curved paths, and this is how Einstein understands gravity. So let me now get to the description of curved spacetime. Here's the simplest example of a curved space, not spacetime, the surface of a sphere. If you look at this line here, which is something like the equator, that describes the shortest path on the surface of a sphere. Whereas if I look at these 2 points at the edge of the smile of this guy, this path is not a straight line, because if I put a string between these 2 points and pull it tight, it'll actually go like this rather than like that. Yeah. So in a curved space, the shortest paths play the role of straight lines. So I'm going to show you some amazing things that happen in curved space. Just open up the envelope and you can do this experiment with me. There are 2 sheets of paper inside. One of them is 3/4 of a piece of paper. And what I will do is to just put the 2 O's together and form a cone. Then you'll find that you have a triangle A, B, and C. This is a straight line, that's a straight line, that's a straight line. Yeah? And on the surface of a cone, you have a triangle, and every angle of the triangle is 90 degrees. You can just try it yourself. Pull out the envelopes that were distributed and show it to people around you. You can actually produce a triangle with 3 right angles. So the sum of the angles of a triangle is 270 degrees rather than 180. So the excess angle over 180 is an example of the curvature, is a symptom of the curvature, which is all concentrated at the apex of this cone. So the next time you eat an ice cream, just look at your cone and realize that it's a curved surface. All the curvature is concentrated at the point here. The rest of it is just paper and it's flat. And the opposite extreme is where the curvature is uniformly distributed as on a sphere. Here it's all at a point, and here it's uniformly distributed. Now, another thing that happens with curved space is that I've got here a picture that looks like this. If I put the two O's together, what I create is a figure which you will not see in a flat space. It's a biangle. This is a polygon which has got only two angles. This is one line, and this is the other straight line. A and B are the two vertices, and they're connected by one straight line here and another straight line here. So in curved space, you can have two straight lines intersecting each other twice. All these things happen in curved space, and in fact, you can see that there's a idea called gravitational lensing, where you'll see the same galaxy at 2 points in the sky. Very good, yeah. You can see that, right? Now, this is an artist's impression of curved space-time. It's actually just space, but this is a way of putting the idea across that here there might be a black hole or something like that, and space around it is curved. Now, why did Einstein propose this idea? And it's because there's a close similarity between acceleration and gravity. It's really the same thing. When you're standing, you feel a force that's pulling you downwards. But when you're in a car that's surrounding a curve, the same force seems to pull you sideways. So gravity can be eliminated by yielding to it. If you're in free fall, you don't feel gravity. And gravity can be simulated by acceleration. And if you take two objects and drop them, okay, there are no handy objects to drop, but if I were to drop two objects, you'll feel that you can see that they fall at the same rate. Since all bodies fall the same, the path they follow is a property of the space-time and not of the bodies themselves. So here's an example that brings out the fact that gravity and acceleration are the same thing. This experiment actually shows, instead of doing it here and ruining the beautiful wooden furniture here, I've taken a video of it. So if I take a bottle, and the bottle in question happens to be a mouthwash bottle where I've poked two holes on the sides. If you fill it with water and you hold it, under the effect of gravity, you'll find that the water leaks out in two streams like that. But if you drop it, the water stops coming out. You can see that very clearly now. So you can see the streams of water. And once it falls, there's no water coming out at all. So gravity can be eliminated by going into free fall. And one more experiment, very similar. Here also you can see the bottle up there. So this is an experiment. It's actually an invention of mine. Actually not mine, somebody else's. But it's an invention that will produce energy from nothing. It's a perpetual motion machine. Okay, it's a very simple device. What I do is, I've already talked. Okay, here there's a wheel here, and there's a set of buckets on the left and on the right. The atoms on the left side are painted red because they are in an excited state. The atoms on the right side are painted blue because they're in the ground state. I told you that atoms have different energy levels. So it's clear that if there's an equal number of buckets over here and an equal number of atoms, the left side will be slightly heavier than the right side. So this wheel will start spinning in this direction. But what you normally expect is that all the red atoms will come to the bottom and the blue atoms will go to the top. That would look like the end of the whole story. But I'm smarter than that. What I do is I take the photons. When the atom is here, I tickle it with a laser and extract the photon and send that photon up here so that this atom gets de-excited. So at any moment, all the atoms on the right are de-excited and all the atoms on the left are excited. That means that always the left side is heavier and it will keep spinning forever and ever. From this I can generate energy and power cities if I like to. What it means is that atoms in a gravitational field are running slower. Clocks in a gravitational field run slower than clocks outside it. Now if you take a look at this picture, here is the height and here is the time. And if I have a clock measuring 1 second over here, when seen from the top here, from another clock, a similar clock up here, it will look like it is 1.0001 second, slightly longer time. Now that is very surprising because I have here two parallel lines. These are the paths taken by light rays to get from here A to D and B to C. These two lines are parallel, and opposite sides of a parallelogram should be having the same length. But you're seeing now that the length of the opposite sides of a parallelogram are not equal. That proves that space-time has curvature. If space-time did not have curvature, it would contradict the first. Basically a proof starting from the first law that space-time is curved. This argument is due to Bondi, a very famous physicist. I just palmed it out of his mind for a short 15 minutes of glory. Now, what is a black hole? It comes in the news a lot these days. So black hole is basically a light trap. To understand a black hole, you have to understand the notion of escape velocity. If this was a regular classroom, there would be a piece of chalk around, and I would throw up a piece of chalk at a certain speed. It would go up to a height and come down. If I throw it with more speed, it will go higher and come down. If I throw it with sufficiently high speed, it will actually escape from the Earth's gravitational field. That speed turns out to be about, I think it's about 11 kilometers a second or some such thing. Now, what happens if I have an object which is so heavy and so small that the escape velocity is equal to the speed of light? It means that light cannot escape. So that's what defines a black hole. That's an object that's so heavy and so small that light cannot escape from it. In order to make a black hole out of the Earth, you have to compress the entire Earth to 1 centimeter. Not very practical, but in principle, that's what you have to do. And the sun to 3 kilometers. This idea is actually very old. It goes back to Michel, a clergyman in England, and Laplace, a very famous philosopher in France. It was only in 1915, because of Schwarzschild, that it was realized that there are solutions of the Einstein's equations describing black holes. But it was not realized by Schwarzschild. It was realized much later. And work of Chandrasekhar, an important Indian astrophysicist American astrophysicist of Indian origin. He was studying the stability of white dwarfs, and he realized that stars are compressed by gravity and held up by pressure. But the pressure cannot withstand the gravity if the mass of a star is more than 1.5 times the solar mass, approximately. And this pressure is actually due to quantum mechanics, the things that were studied by Chandrasekhar. And he really put forward his ideas, but nobody listened, because there was a very, very famous astrophysicist called Eddington who disagreed with his views. So there was no good reason for disagreeing with his views, but it was an opinion rather than an argument that Eddington had. But much later, in the 1960s, people discovered that there were very energetic sources of energy in the universe. And these were traced to black holes. In the late 1950s, enormous energy was seen from a small region, about 1,000 times the luminosity of our galaxy, from something as small as the solar system, which is 1 light day in size. Now, it turns out that black holes are good sources of energy. And to understand this, all you have to do is to reverse the argument of escape velocity. I have to put in a huge amount of energy into a stone to make it escape from the Earth. Now, if I reverse the argument, if I take in a stone from infinity up to the surface of a black hole, the same energy will be released. And that energy is equal to mc squared. So black holes are very good sources of energy. And you can, if you're near a black hole and you find that is, and if you take an object which is emitting a fixed frequency and throw it into the black hole, you find that there's a Doppler shift and there's a red shift. All these things are there. And let me have the second mathematical demo. Yeah, just come down here and click on this button here. You'll see this is a fixed frequency, similar to the one that just now failed me. Anyway, this was just supposed to be a fixed frequency. So you'll hear yes, that's what you'll hear. If you hold the source near your ear, that's what you'll hear. But now if I throw it into the black hole, what you'll hear is in the next slide. Over here. The same object, as it's falling in, gets Doppler shifted and red shifted, the effects that I talked about earlier. And you'll hear a sound that sounds like this. And then after that, nothing. The thing has fallen into the black hole. Yeah. Now I'll just finish the Mathematica slides. Can you go to the end? Yeah. This is another perpetual motion machine working on a different principle. And I'm going to show you a little later that rubber bands actually contract when heated, unlike metals. So if you look at this wheel, this part is cool and that part is warm. And because this part is warm, the rubber bands on this side are going to be contracted slightly, and that moves this over to the right. The wheel will shift to the right, and you'll get a difference between the gravitational field on the two parts, and you'll find that this hoop is rotating. So if you have two different temperatures, you can actually make you can actually make an engine that converts a temperature difference into motion. So that's the point of this one. So I don't need the Mathematica anymore. Yeah. So is this clear that you can make if I have a wheel and rubber bands, I can actually make a temperature difference into a directed motion. I was talking about astrophysical sources of energy being black holes, because black holes can generate a lot of energy, but actually the efficiency of black holes for converting mass into energy is very low. It's only about 5%. You can do a much better job if you were to control things better. So here's an example. Suppose we were to find a black hole somewhere here, and we are here on planet Earth, and we take a mass, a block of wood or metal or something, and I use a pulley and rotate and use the pulley to lift up a weight on the Earth. So I extract all the energy from the block as it's going in. As it goes in, I can extract all the energy, which is equal to mc squared, from this block, and when it reaches the horizon, I just let it fall into the black hole. And I've got this much energy. A black hole is a machine for converting mass into energy with 100% efficiency. So if you just throw it in, you lose all that energy, but if you do it in this controlled fashion, you can extract energy from a black hole by throwing in matter. And this is roughly how energy is produced in a black hole in a quasar, for example. So in relativistic astrophysics and relativistic cosmology, we find an inefficient version of this same process. Now, if you look at a black hole from the outside, what you see is that beyond a certain point, you cannot see. You cannot see beyond a certain point. That's called the event horizon. And from the outside, what you find is that things that you throw into a black hole seem to go and get stuck at the horizon. They don't really fall inside. But from the inside, you get pulled in. And as you get pulled into the black hole, your body gets stretched by gravitational forces. So if you're falling in feet first, your feet and head are pulled apart because the gravitational force is different. And sideways, you get stretched. I mean, you get compressed sideways and pulled in like this. And what will happen as you keep falling inside is that every atom will be ripped from every other atom in your body. And finally, every proton and neutron in your nucleus, the nuclei, will be ripped apart. And you'll end up with a mess of stuff inside. So in some sense, black holes are the edge of space-time. We really don't know what happens at a singularity. The singularity is the point at which the black hole, which is at the center of the black hole. And this is something like the edge of the Earth. Remember when the Vikings were exploring the Earth, they thought they'll come to the edge of the Earth where the ocean ends, and there would be terrible things happening after that. That's exactly the state in now, that state that we are in now. When you get to the singularity, all of physics breaks down. We don't know what will happen after that. So this is what a black hole looks like from the movie Interstellar. A black hole is over here, and there's a disk around it. And there's a disk which is like a flat pancake. But because of the light bending around it, which can happen around a black hole, you see the disk both below and above. This is the light that's coming to us from under the black hole. This is the light that's coming to us from above the black hole. And here you see a ring, which is the last rays of light that just graze the surface of the black hole and come to us. This is another picture of a black hole that was done in 1970s. Somebody used a very primitive computer at that time to figure out the way a black hole would look. Here what you can see is that the part of the accretion disk which is coming towards us looks brighter. This looks dimmer because the energy is all focused away from us. Now, I'm talking about heat engines. Environmentalists tell you to conserve energy. Yeah, everyone has heard this. Switch off the lights when you leave the room. I've seen signs of this kind in the labs also, that will the last person in the room switch off the lights and turn off all the air conditions and things like that. That's what environmentalists tell you. Now, physicists tell you that energy is conserved, that there's no destruction of energy. Why would you need to conserve energy if it's anyway conserved? So, can I have an answer to that? So energy is always conserved, but it can be wasted. And what does it mean to waste energy? It's to convert energy into heat. Heat is degraded energy in the sense that heat has molecules going every which way. Whereas if I take a cannonball and throw it in a particular direction, it's organized energy. All of it is going the same way. I can try to extract that energy from the cannonball. You cannot extract energy from a system which is at a single temperature. It has got everything moving in many different directions. You can extract energy from a system which has got a difference of temperatures, as I showed you with the other thing, but you cannot convert heat to energy completely. So the second law of thermodynamics, the first law was already referred to by this gentleman here. The first law tells you that energy is conserved. The second law tells you that energy can be wasted, that you cannot use all the energy. I mean, you cannot use, you cannot convert heat back into energy. That there are two kinds of energy: useful energy, which can do work, and useless energy, which cannot do work. So these are the two laws of thermodynamics. And actually, the two laws of thermodynamics are more sacred than any other laws of physics. I mean, any physicist will tell you that he'll be willing to give up almost anything, but these two laws he will be glad to be burnt at the stake for. The answer that was given by this gentleman here is that heat is a degraded form of energy, disordered molecular motion. So we can convert electrical energy into light and kinetic to potential, and that's the first law of thermodynamics. Energy is conserved. The second law tells you that you cannot completely convert heat into work. That is, once you convert it into heat, there are limitations in how much you can get back into useful energy. Energy is conserved, but it can be wasted. Converting ordered motion into disordered motion is a waste of energy. So is this point clear? This is, in fact, the most important point I want to make. Now, there's a word that is might be new to some of you. The word entropy is a measure of disorder. And basically, heat is disordered. Disordered energy is called heat. And entropy is a measure of the disorder. And a fridge, for example, works by taking energy and moving heat from a colder temperature to a hotter temperature. Normally, heat flows from hot to cold, but a fridge works in the other way around. And to do that, you need to put in some energy. That's the functioning of a fridge. Now, what you might ask is the relation between disorder and heat. And this is very easy to demonstrate with a simple experiment. In the envelopes that you got, you'll find a rubber band, or 2 or 3 or 4. So what you do, a rubber band is a polymer. Rubber is a polymer. It has lots of long molecules. And if I pull it straight like this, all the molecules are lined up like a string, straight like that. But if I contract it, the molecules are all in all directions. And you can convince yourself that a pulled polymer is more ordered than an unpulled polymer. This is more ordered because everything is pointing the same way. This is less ordered. Now, the connection to heat comes like this. You pull out the envelopes and you take the rubber bands, put it on your forehead, and rapidly pull it tight. When you do that, you'll find that the entropy is thrown out from the rubber band and your forehead feels hot. Let it go, you feel cold again. Hot and cold. Just try it out. So that's the connection between heat and disorder. Disorder is basically a sign of heat. So here's an example. This is a slinky, and up here you can see this slinky was lent by A to B, who went and made a mess of it. And this part of it is ordered. It's in a nice regular motion. It looks like a helix, and up here it's disordered. There are many more ways in which it can be disordered like this than it can be ordered like this. And the multitude of ways in which can be disordered is what we call entropy. So closed systems have a fixed total energy because of the first law of thermodynamics. This energy will tend to dissipate into heat. The final state that we expect will maximize entropy for a given energy. This is what we call a thermal state, and it has a temperature. We cannot extract work from it, but we can extract work from two thermal systems at different temperatures, and that was the heat engine I showed you earlier, when I have two different temperatures and the rubber bands between them. There's another example here. This is called a Stirling engine. So it consists of a wheel here, and the wheel is in contact with the atmosphere. And the bottom here, there's a chamber here which has got air in it and a piston. The bottom is in contact with ice. This part is ice. And the top is in contact with the air. And that's a temperature difference. And this can be used to convert a temperature difference into directed motion. That's what a steam engine also does. So you can see that the temperature difference is converted into the wheel spinning in one direction. And now what I'll do is I'll remove the temperature difference by keeping it out there. And I'll show you the ice that it's standing on. This is some foil here to encourage conductivity. So you can see that the machine is starting to wind down slowly. It's like a marathon runner. As he gets to the end of the race, he starts getting more and more tired out and finally grinds to a halt. And all that has happened is that I've removed ice from under it. Now, ice is cooled, and you might think it has got less energy. And there's some paradox here, but no. The engine is running on the difference between room temperature and the ice. You can see this is ice here. And I think it's come to a grinding halt at some point. So Now I can come up with a new use for black holes. I'm going to make use of the fact that the black hole, I can throw things into a black hole. Now suppose instead of throwing a block of metal into a black hole, metal is a valuable thing. I take the entire garbage produced by Bangalore City and I compress it into a small orderly rectangle and I'll lower it slowly into a black hole. Now garbage has entropy. I'm sure you agree with that. No? It's very disordered stuff. So I can throw disorder into a black hole, and by doing this I can decrease the disorder of the universe. This looks like I can use black holes to violate the second law. So you seem to, there's then no bottom to this. I keep violating laws all the time. I try to do the first law, the second law, and now I'm trying to violate the second law again. So if I could do this, if I could take the garbage of Bangalore and convert it into useful energy and get rid of the garbage also, I would get a Nobel Prize for that, right? But this would violate the second law of thermodynamics. To avoid violating the second law of thermodynamics, we have to say that the black hole also must have entropy. There's no other way out. Because I'm throwing things into a black hole, and if the black hole didn't have entropy, then the entropy of the universe has decreased, because I can never access what is inside the black hole. On the other hand, if I say that the entropy has the black hole does have entropy, I can say, okay, I decrease the entropy of the universe, but the entropy of the black hole is increased. So I'm forced to assign entropy to black holes. And it turns out that people who've studied this subject tell you that the entropy of a black hole is geometric. It's proportional to the area of the black hole. The event horizon has a certain area, and that is the amount of entropy that the black hole has. Now, it has also been shown that the total area of a black hole, of black holes, always increases. If I have two black holes, they fall into each other and become one big black hole. And the total area of the new black hole is more than the sum of the areas of the initial black holes. So, black hole areas behave in the same way as entropy does. And the identification of the area of a black hole is a firmly established fact in theoretical physics. Now we've come to the idea that black holes are thermal objects. They have an entropy, so they could also have a temperature, which is closely related to entropy. Black holes are thus thermodynamic objects and so have a temperature as well as an entropy. Like all hot bodies, they must radiate energy. And this was shown by Hawking in the 1970s, that in quantum physics, black holes are not black, but glow with a small temperature, which is inversely proportional to the mass of the black hole. And that's called Hawking radiation. Now, Hawking's striking insight in quantum theory that black holes radiate has really put theoretical physics in a bind for about 40 years now. It has led to deep connections between gravitation and thermodynamics, and this is the subject of current research. We don't know the answers to any of the questions you can start to ask now. So, to summarize, black holes are macroscopic objects with a microscopic description. I can write down precisely the nature of the black hole spacetime using GR. Current research addresses the following question: is information lost in black holes? And this is called the information paradox. There seems to be a definite conflict with quantum theory here. Quantum theory tells you that nothing is destroyed, information is always conserved. And it's turning out that black holes can be used to destroy information. You can take a dictionary and throw it into a black hole, you've destroyed all that information. You can commit a murder and throw the body into a black hole, you've destroyed that much information. If any of you are thinking of committing murders, well, this is one way of doing it. So one of the questions is, where are the degrees of freedom responsible for black hole entropy? Normally when we have entropy, it has to do with some degrees of freedom which are all uncorrelated with each other, like molecules. Are they stuck at the boundary? Is there new physics beyond GR? And this new physics is believed to be quantum gravity, or perhaps it may be a unified theory that takes all the forces of nature and puts it into one. All these things are being pursued with very little success, to be honest. There's a lot of activity, but not much progress. This has been going on for about 40 years now, maybe more. So let me just conclude this talk by saying that science is the combination of imagination and skepticism, and you need both to make progress. You need imagination to think of new ideas and new ways of looking at old things, new perspectives. And you need skepticism in order to test those ways and weed out those ways of looking at nature which are not true or which can be disproved. And in fact, sometimes the trouble in this field is that it's very hard to disprove ideas because the experiments are so difficult. You can't really get a black hole and do experiments with black holes.